This is Lecture 7 on the Mechanics of Growth, and my name is David Bishai. Let me tell you about the outline for today. We're going to cover critical concepts in growth theory. The first one is going to be the basic fact of diminishing returns to scale. Then we're going to go through several different niche models, and each of them will be celebrating a very different policy prescription. There will be the classical and the Coale-Hoover model, which highlight the role of family planning and population control. There'll be Coale-Hoover, Harrod-Domar, and Solow models, which highlight the role of savings. The Lewis model highlights the role of industry. And we'll end our lecture with human capital-based models, also known as endogenous growth theory. Now, there's a lot going on in this lecture, and the best way to survive it is to not get obsessed about understanding all of the math. And I want you to go back to focus on these key concepts. There's diminishing returns. These models each have a focused policy implication. And ultimately, each model is limited in some way. So let's start this tour of growth theories. First idea is that capital can grow exponentially. Capital is something that can help make more of itself. But this does not always happen in human history. Exponential growth of capital requires the right conditions. It requires that all of the other inputs besides capital, inputs like land and labor, are obtainable in sufficient amounts. It also requires a stable society so that the capital keeps getting saved. People won't save in an unstable economy where they don't feel their savings will lead to any improvement in their livelihood. So one graphical version showing the idea that there can be exponential growth is this box and arrow model showing capital Y, which is output in the circle in the top left, that feeds back into the growth of capital in the central rectangle. The capital also contributes to the growth of the economic output, capital Y. Then in the middle, when we want to see how the capital stock is governed, we see capital inflow, which is coming from a savings rate times the economic output of the country. And remember, the economic output, capital Y, equals technology times labor to the 1 minus beta times capital to the beta. So the input into the economy, into the capital stock, is governed by STL to the 1 minus beta K to the beta. The outflow of the capital stock is simply depreciation rate delta times capital. Now, just for simplicity, we're going to assume that beta equals 1, and we're going to say that the capital stock in the next year is the capital stock last year plus the savings rate times TK T to the minus 1 minus delta K T to the T minus 1, which is last year's capital. The change in capital is proportional to capital, and that's really one of the big requirements for predicting exponential growth of anything. So the growth models all recognize that there can be this positive feedback loop of capital to more capital. And now let's just start going through them one at a time. First, the classical model, which was the first model to recognize that there can be and will be diminishing returns. Then we'll go on to the demographic identity, which led to both Harrod-Domar and Coale-Hoover's recognition that the denominator of population was a critical problem. Then we'll focus briefly on the Lewis model, which showed that in a developing country there can be dual sectors, both an agricultural sector and an industrial sector, and the migration between the sectors was the critical focus for Lewis. We'll go on to the Solow model, which is a more sophisticated version of the classical model. We'll test the Solow model and find that we actually need a better model, and we'll end the lecture with endogenous growth models. So first, the classical model, where we first recognized that there were diminishing returns. The idea is that agricultural products are made from inputs, land, labor, and capital. And if you were thinking about America in the colonial era, there was unlimited land, and the colonists come to the East Coast and they start making farms, and they could double the amount of farms and double the amount of corn. If you double the land and the labor and the capital, you'll double the amount of corn. The economists in England did not have unlimited land, and they were living at a time where land was fixed. And they saw that if they did not increase the amount of land and they just doubled the labor, they got less than double the amount of corn. They also saw that if they doubled the amount of machinery, of horses and plows, they would not double the amount of corn. So on and so forth. You have to have everything double to double the amount of corn, and so if you hold one of the inputs fixed, you will not get constant returns to scale. You'll get diminishing returns to scale. So in a graphical version, here we have the economic output Y on the vertical axis and an input capital K on the horizontal axis, but we're assuming we're going to hold land fixed. And so we get diminishing returns to capital because we're not doubling the amount of land. The exact same thing happens to labor. If we hold the amount of land fixed and increase the amount of labor working on land, we do not get constant returns to scale. The amount of corn we get off of our land starts to diminish despite increasing amounts of this input, either capital or labor. So the classical model says that the inputs are land, labor, and capital, and notes that there are diminishing returns to scale. So the idea here in the middle of the slide is that the production function f says that the amount of corn comes from a function combining capital, labor, and land. Land is going to be capital D, and it's a function with diminishing returns to scale. And I've drawn it here on the right-hand side of the slide, and look, it's just as before, diminishing returns to scale. Now, I've drawn also the need of labor to eat some of the corn. And every time we get a new worker, we get the same exact need for corn. So if we increase workers by a factor of 2, from like here to here, we would double the amount of corn. So subsistence consumption does not have diminishing returns. It has constant returns. We need to keep feeding our workers every time there's a new worker. And there's the problem that we come into in the classical model. We have this diminishing returns to scale in our output, but labor, as it grows, keeps eating more and more of the corn. Well, this leads to this dismal conclusion that we know of from Malthus, who was one of the classical economists. In Malthus and other classical economists, we saw that the economy would hit this stagnant state. Now, let's talk about what's happening here on to the economic surplus. The economic surplus exists while the output is higher than subsistence. This little lens-shaped area where there is more output up here than subsistence consumption means that there's a surplus that can be used in the economy. The classical economists focused on who would get that surplus. They thought that, well, the capitalist who was owning the plows and the oxen might need some of the surplus. But they also saw that the landlords would typically ask for some of that surplus. The classical economists really liked the capitalist. They saw the capitalist as actually using their surplus to make more oxen and plows and machinery. They liked capitalists, and they noticed that capitalists would have this positive feedback loop between their investment and the size of their economic input. They did not like the landlords who just took their economic surplus, but they did not increase the amount of land. For classical economists, landlords were parasites, just taking the surplus and not making the economy get any bigger. Now, what Malthus told us is what's on this graph, which is that there's this pressure to the right, that if you're sitting, let's say, here in the middle of your economic growth time, and you've got all of this money, Malthus said if you give any of the surplus to labor, if you cut them in on any of this, they're going to have babies and going to move to the right. And suppose we're over here, and if you give any of the surplus to the workers, they're going to have more babies and we're going to move to the right, and the workers won't stop having babies until you starve them right here at this ultimate endpoint of classical growth, where we're stuck. This is stagnant, where we have a pretty big economy. We're producing lots of stuff, but we have lots of people, and everybody is just starving, just getting enough food to keep their body alive for one more day working in the fields. So a very dismal picture of classical growth. Development in the classical model ends at the stationary state, where wages are remaining at subsistence. The economy has no other way to go forward. Now, even if there is a technology shift, supposing we say, hey, let's invent a steam engine or something, and we've lifted up their economic productivity to much higher levels for any given amount of labor. Thanks to this wonderful technology, like the steam engine, the economic output is great. But Malthus says, doesn't matter. If you give them more output to the laborers, they'll have more babies, and we're going to still end up in the stationary state. It just doesn't matter. The only way forward is to just keep on racing the population with your technology growth. So every time there's a new baby, we keep on bringing up new technology, and we keep hustling forward to keep ahead of this trap of the stationary state. So in the classical model, growth occurs because the capitalists were saving. The capitalists were the one input where having some of their thing, capital, made more capital. Now, labor makes more labor. However, labor eats the corn and capital doesn't. So if you want the economy to grow, we have to encourage the capitalists to save. Now, growth is pointless, say the classical economists, because everybody's going to end up no better off than when they started. This is still a useful model because there are still places that are in these traps where they have had so much population growth and so little technological innovation that they are at subsistence wages. We call these places poverty traps or Malthusian traps, and they're places where giving them new technology isn't going to be enough. One requires a fundamental change in their economic model. And we should reflect briefly that there were very few poverty traps and Malthusian traps. And escape from stagnation, escape from that stationary state, has been the common experience of most countries. We'll come back to that. But I want to go on and talk about one of the first ways we theorized a solution to get out of the poverty trap, and that was through demography. So I want to move on from the classical model to the Coale-Hoover model and start with this demographic identity. Many of you are familiar with the basic algebra, where if you simply define GDP per capita as capital Y divided by P, you'll get the identity at the top of the screen. But then if we start doing a little bit of algebra, we take the logarithm of both sides. We realize that log of a quotient is the difference between the logs. And so now we have the log of little y equals log of capital Y minus log of P. This is just algebra. Then we take the derivative on both sides, and we remember that the derivative of a log is equal to 1 over the value inside. So d log of y is the change in y divided by y. D log of capital Y is the change in y divided by y, and so on. And so these really are growth rates. And once we know this, we can say that the rate of growth of GDP per capita is by definition the rate of growth of the GDP minus the rate of growth of the population. So what are the implications? Well, you don't want your denominator to grow. And so if GDP per capita has population in the denominator, we want the denominator to grow slowly. The implications of the Coale-Hoover identity are to focus on making family planning methods available, using education or other measures to delay the age of marriage. But clearly you want the numerator to grow fast. How? What can we do to make the numerator grow fast? The classical economists realized that saving was a big part of that, and Harrod-Domar are going to come along in the Harrod-Domar model in the 1940s to focus on savings. Now, the theory of savings isn't very sophisticated right now. It's just that you save a portion, little s, of your income. So in Harrod-Domar, the people in the economy get their corn or their economic output, capital Y, and they save a proportion of it, 10%, 20%, who knows. Now, that savings is used to fund investment, and so we equate investment, capital I, with savings, capital S. Now, the rate of growth of income is proportional to investment. This is shorthand for something that we've seen and we'll see in more detail in the Solow model, that capital makes more of itself. In Harrod-Domar, there's this factor called kappa, and that's related to the quality of the capital that one has chosen. So in Harrod-Domar, the rate of growth of the GDP is proportional to the savings proportion, little s, and 1 over kappa, which is the quality of investment. So the notation's given on the right. S is total dollars, I is investment, little s is the savings per unit of GDP, and kappa is the incremental capital output ratio. And when 1 over kappa is big, the capital is being invested in high quality capital, which is going to make the economy grow. So we're going to now combine our insight with both Harrod-Domar and Coale-Hoover, and we're going to put the Coale-Hoover S over kappa in place of R sub big Y. R sub big Y equals S over kappa, as you can see in the top of the slide. And this is an equation that says we want to do 3 things to make the economy grow. If our goal is to make the rate of growth of GDP per capita, that's what this is, rate of growth of GDP per capita, we want to have R sub P to go down, we're pro-family planning. We want the savings rate to go up, we're pro-savings. And we want 1 over kappa to go up, we want kappa to go down, we want to make sure we're investing in good technology. So these were the policy prescriptions that you would hear in the 40s and 50s. Save more, get good capital, and have family planning. I want to move on to the Lewis model. This is our third growth model of the day. And the Lewis model is going to talk about the supply and the demand of labor, and Lewis is going to recognize that labor is going to migrate from the agricultural sector to the industrial sector. So first off, let's just talk about where we are right now. We know that we have a relationship between the economic output and these inputs, and that there is diminishing returns to scale. So if we have economic output, capital Y, we know that every time we add more labor, given fixed land or fixed capital, the slope of the economic output function gets smaller and smaller. Now, if I just graph the slope of this curve, it's going to start very big, get smaller. The slope is smaller, and here the slope is very small. It's close to 0. So now I'm going to just graph that slope for you on the right hand of the curve, and we see, as I predicted, that when the number of laborers is very small, the slope of their economic production, or the wage, is very high. The wage is how much we give them. The reason we equate the wage with the slope is because we want to pay inputs how much extra they give to the economy. The idea is that if one is very productive and helps the economy grow a lot, one should ask for more. Whoever is hiring a laborer in this part of the production process notices that one extra labor is going to give them a lot of extra capital Y, and they will want to give them more. An employer who is hiring a laborer over here notices that that extra laborer has almost no extra value added to their economic output, and they will not be willing to offer them a higher wage. So that's why we notice that when there are very few laborers, the wage can be very high, and when there are many laborers, the wage will fall. Now let's go on and talk about the differences here, because we notice that we can have two wages at the same time. We can have an industrial wage, which is very high because that industrial employer actually has some capital and notices that every new worker gives them a pretty decent return on their wage. Meanwhile, out in a rural area, out in the agricultural economy, without a lot of capital, it's very labor intensive, and there are a lot of laborers out in this agricultural area at most moments in history. So out in agricultural zones, the wage is much lower, and in the industrial zones, the wage is higher. Now, in this Lewis model, what we're going to notice is that there are a lot of people out in the rural area, and Lewis calls that the reserve army of the unemployed or underemployed. He's noticing what many of us have noticed, which is that in a lot of rural areas in low-income countries, you'll have many people doing one job. If you need to dig a hole, you'll see one guy with a shovel and three guys watching him dig the hole, and they're all going to be working and trying to split the returns from that day's economic activity. So lots of use of labor without really being very judicious about applying it as though it were scarce, because it's not scarce. So we have this idea of there being two wages at the same time, a subsistence wage and at the same time a industrial wage. Now, one thing that I have going on at the bottom is this idea of Albert Schweitzer that one needs to think occasionally of the suffering of which you spare yourself the sight. And this quote just sort of makes us bear in mind that very often we focus on only one side of a model like this. The industrial workers often lose sight of the existence of the agricultural workers and don't realize that they're sharing the same economy. So let's move on to the supply side of labor. Because of Lewis's reserve army of the underemployed, for many parts of the growth of their economy, the wages are flat. As we move our quantity of laborers from the left side of the graph, from very few laborers to more laborers, because there are so many workers in an agricultural economy, they don't actually see any change in how their wages would go as they supply more. They're willing to enter the market without requiring a higher wage. However, after a time, after we've reached the end of the model, workers are finding that they won't enter the market until they are given extra wages. So the supply curve of labor, how much people would need as a wage to enter the labor market, is flat, and then people say, no, I won't enter the labor market until I am given a higher wage at the end of the market. So that's Lewis's model of the supply side of labor. So now what we're going to do is combine both the supply side and the demand side, and we have in this combination an idea where we will have some migration. Here we have that the total amount of labor is put into two compartments. There's the formal sector labor in industry and the service sectors of the cities, and then there's the supply of labor in the agricultural setting. And let me go back. In the agricultural setting. And there's some migration where the people in the agricultural setting are trying to move into the formal sector. We also have the idea that the wages are somewhat higher in the formal sector because there's more capital in the formal sector than the agricultural sector. So we start our model here at D1, where there's just this much demand for labor, and we notice that we have more people working in agriculture. We have this quantity of people in agriculture, and we have a fewer number working in the formal sector. And because the wages are higher in the formal sector, not shown in the model, but in the back of our minds, is this idea that there are workers moving from that agricultural sector to the formal sector. And so we let time go forward. We get on to demand 2. By that time, we have had many, many more people move into the formal sector. Their wage is not getting any higher. The formal sector in the city absorbs these workers, does not have to pay them a higher wage because there's just so many of them, and the economy keeps on rambling ahead. Finally, wages might start to rise in both the agricultural and the formal sector because this last part of the curve shows that the workers require more income, more wage offers in order to come into the model. So this idea that there are workers moving from the agricultural side to try to get those higher city wages is what we attribute the Lewis model to telling us. So the predictions of the Lewis model is that there will be urbanization. Economists who read the Lewis model also said it's great to have industry. Something in industry is leading to the process of growth, and we want to focus our policies on making our country safe for industry. This model actually has this dark side where it leads some to neglect the agricultural sector. Lewis has influenced economists to think that the agricultural sector is backward and inefficient, unable to innovate, and a Lewis economist would say that growth depends on moving people outside of that rural sector and into the cities. Let's move on to the NeoClassical growth theory. I want to recall our equations. We had before, we've seen an equation where the economic output, y, at time t plus 1, would depend upon values of capital and labor in the past. In the NeoClassical model, we add to that an idea that technology is moving, and it's moving as an exogenous function of time. It does not depend on capital or labor at all. According to this NeoClassical model, scientists and engineers just keep figuring out things as the calendar rolls by. That's the only reason they discover things, is that time has moved forward. So with this equation, we also want to remember that these exponents beta and alpha are going to be the drivers of the output of each of these. Alpha and beta are between 0 and 1, and they sum up to 1. So alpha equals 1 minus beta. It's also true that both alpha and beta are parameters measuring the marginal productivity. When beta is very big, it means that labor is very productive. When alpha is very big, it means that capital is very productive. And since they sum to 1, the NeoClassical growth theory says that one or the other is going to be more productive than the other. The nice thing about this equation is that it allows substitution between capital and labor and technology. The equation allows you to get the exact same GDP per capita from very different amounts of technology, capital, and labor. You could have lots of labor and little capital, lots of technology and little capital and labor. And all of them could still result in the same amount of GDP. Now, I want to notice that there is some mathematics, and in a hidden slide with this lecture, if you can get the PowerPoint, you'll see a whole slide full of algebra deriving several facts from this assumption up at the top of the slide. For one, we can conclude algebraically that the rate of growth of capital per labor, the capital-labor ratio growth rate, will be proportional to savings minus the rate of growth of the population, the rate of growth of labor times the capital-labor output ratio. So if we have a high rate of population growth, we need to have a high savings rate. That same idea from Coale-Hoover is sitting in this model. I also want to preview, or just park in your memory briefly, that the model predicts an equation for the rate of growth of GDP per capita. Why do countries grow at 3%? Well, if that rate of growth of 3% is 3%, that 3% is equal to two terms: the rate of growth of technology plus an algebraic combination of savings rate, current GDP per capita, technology, minus the rate of growth of population. Still, our fact remains that the rate of growth of population is dragging down the rate of growth of GDP per capita. So we're going to come back to that internal anatomy of the prediction for growth. It's going to matter a lot to us in just a minute, but I wanted to park it there. I don't want you to feel like you have to do the algebra that derives it. If you want to see this derived, my advice is to open up the hidden slide and look at it, but you don't need to. I want to get through the idea that inside this neoclassical growth theory remains our initial idea of exponential growth. We saw this at the beginning of the lecture, that capital is used to make more capital and that capital depreciates. So sitting inside the Solow growth model is that same old classical idea of the stagnation point in the middle. Now, what we see here in the Solow model is a production function in the middle called S times little y. That's the rate of growth of the economy. So the rate of growth of capital per labor is equal to S times Y minus RL times K. The negative part comes from population growth. The positive part comes from the growth of capital. It really looks a lot and is a lot like our old Malthusian trap. So here's a point where the economy won't grow. Here the negative part is higher than the positive part. This is where we are going to get stuck in the Solow growth model. Now, I will notice, and I want you to notice, that rather than this being subsistence wages, this is simply the drag on the growth of capital over time. So while this is saying is that this new stagnation point, rather than being starvation, is simply a point of zero growth of the ratio between capital and labor. It's still zero growth. It still says that we're stuck. We're not going to have any faster rate of growth in capital per laborer. It's going to be zero. And the Solow model says we are going to hit a point where all of the capital per labor that we have around us now, if you have 2 robots per person, you're always going to have 2 robots per person. The number of robots per person, this capital labor ratio, isn't going to grow anymore because we'll have hit this wall and have hit our new end of the stagnation point. So it's very comfortable for people who grew up on the classical model. It has a lot of testable predictions, and in fact, that's what economists did with the Solow model. They began to take it out to test it. So To the left of the stagnation point, the capital-labor ratio grows. To the right, the capital-labor ratio shrinks, and the model predicts that we will be in a point of stability with a constant amount of capital per laborer. Now, the Solow model had several implications. One of them was that these factors of production, technology and capital and labor, would move to where they were most useful. It assumes that technology instantly moves, that there's nothing holding it back from moving around. It assumes that the best technology is equally available to every capitalist and worker anywhere on Earth. Now, that's a false assumption. If you think about where the technology of the world is centered, it isn't everywhere. There are places that do not use the best technology, and those are interesting reasons, and we'll come to that later in the course, where we think about innovators and entrepreneurs who would want to move technology to a place, and obviously they worry about the stability of their entrepreneurship and whether the government will fall or try to take away their investments. So technology doesn't move freely. It's often embodied in capital, and it requires entrepreneurs to move it. The second assumption in the Solow model is that capital should earn higher rents in places where capital to labor ratio is low. So where there's not a lot of capital, we should see bankers lining up to try to send capital. In Ouagadougou, where there's not a lot of robots and capital, we should see Wall Street bankers lining up at JFK Airport trying to take capital to Ouagadougou. Now, they don't, and it's the same reason that the Wall Street bankers do not believe that Ouagadougou would be a safe place for their investments. But the idea still remains that if you can find a government that has very low amounts of capital and can promise you and assure you that your investment will be safe, capital should go there. The Solow model says that capital and technology should move to places where they are more productive, and that will lead to convergence in growth rates. That places that have a lot of capital won't get more capital. People don't want to put more capital where it's not going to give them as much of a return. So this idea of convergence, where the capitalists will try to take capital to places that need capital and don't have a lot of capital, says that the growth rates around the world should converge and they should begin to be more similar over time. Lots and lots of tests of convergence. There are two versions of the convergence hypothesis. Version 1 says that the rates of growth around the world will all become similar as capital goes to where it is most useful. Version 2 is even more stringent. It says that rates of growth will be highest in the countries with the least capital and lowest in the countries with the most capital. So USA, which is drowning in robots and machines, should have a very low growth rate, and Mali or Burkina Faso, where there are not a lot of robots and machines, they should have a very high rate of growth because all of the capitalists should be flocking there to take them capital. Now, poor countries should eventually catch up, and the degree to which the poor countries do not catch up is an indication of governments that do not make investors feel secure. So there have been a lot of attempts to test the Solow model's prediction of convergence, and during these tests of the model, there were several discoveries, and I wanted to briefly review the main discovery. So when one tests the Solow model, if you go back to the prior slide, you'll see that one can take a logarithm through the y equals t, k to the 1 minus beta, l to the beta, and if you just linearize it, as is shown on the slide, by taking logs, you can go through the country's data and run regression and estimate a value for beta. And this is how an economist would do it. They would take a set of 150 countries, decide how much capital, how much labor was in each country, hold on to technology as a residual term, because we don't know how much technology there is in the world. We don't know how to measure it. But we estimate the capital stock, we estimate the labor supply, and we know measures of the GDP, and we fit statistical regression. What happened in this line of work was, first, the R squared was low, meaning that we could only account for about 1/3 to 2/3 of the variance in this GDP per capita. So the residual, whatever it was that was contributing to variance that was not in the model, was called the Solow residual. And economists believed that the Solow residual was technology. But if you remember your statistics, it's a residual. Everything is in there, not that thing. So this common claim, after people noticed that the Solow residual was so big, was, oh, that's technology. We should hire engineers and scientists to make technology bigger. But please, class, remember that everything is in there, and there are many contributors to growth besides technology. There is not just what the scientist invents in the lab, but also what a politician or a social organizer can create in the form of civil society and stability and a government that can create law and order. Now, this Solow residual was a powerful determinant of growth. It has its times of growth itself, and in the early 70s of the last century, the Solow residual kind of petered out and stopped growing. So we don't know why, and first the technology people said, I'm going to try to explain what happened to the Solow residual. But these days I think we're much more comfortable believing that there is political technology included in this T term. And when we see growth and fits and starts in growth, we often look for political technology in as much as we look for scientific technology. So the last finding when we started to test the Solow model was that the value of beta turned out to be 0.6. Now remember, in this model, beta is going to be the marginal product of labor, which implies that capital is going to be 0.4, and the marginal product of capital would be 0.4 in this model. Now there's problems with finding that beta was 0.6. If we say that the Solow model is true, and we say that beta is 0.6, we ran into a lot of typical statistical anomalies that couldn't be fixed. So if we accept that beta was 0.6, and we plug that back into the rate of growth of GDP per capita equation, I brought it back for you. I promised I would bring it back. What I'm going to do first is just put 0.6 into the algebra. So 1 minus 0.6 is 0.4. Negative 0.6 divided by 1 minus 0.6 is 1.5. 1 over 1 minus 0.6 is 2.5, and so on. So I now have this equation. What I'm going to do briefly is show one of the typical anomalies that would happen in the Solow model. In 1991, both the UK and Peru had a rate of growth of GDP per capita of 2.4%. But we could put in values of their GDP per capita. For instance, in the UK, GDP per capita was 16,000, and the rate of growth of labor was 0.2. And if I put those values in, I put in my 16,000 here. I put in my rate of growth of labor here. I will put in, for Peru, it was, sorry, not 16,000, but 1,000. I'll put 1,000 in here, and I'll put my rate of growth of labor. It wasn't 0.2, it was 1.9. And what I'll find is a problem, because I'll find that the equation won't balance. I can't get 2.4 for Peru unless the savings rate in the UK is 16 times bigger than it is in Peru. So the model is wrong if we use beta of 0.6. But it turns out that the model would work out okay if beta were smaller and if beta were more like 0.3. So the empirical observations falsified the theory, and the economists working with the Solow model needed a theory that might lead to a beta that was a bit smaller, down to 0.3. So what was used first to fix the model was a model by Romer, who said that, I think technology is endogenous. So before we had technology was just running on calendar time. Under Romer, technology depended on capital and labor. Romer said capital is going to make technology because there's knowledge spillovers. Whenever we create a robot, that robot requires engineers who have to have educations, and that robot will lead to new applications of the robot. So every time we get a new robot, capital K, we're going to improve the quantity of technology. Romer said that labor slows down technology because if you have a lot of labor, you don't work so hard at inventing robots. You just say, well, I'll hire more people to solve the problem. So the idea is that labor is coming in with a negative exponent, negative gamma. But if you just look at this, if we have a negative gamma sitting here in the technology spot, and we multiply L to the negative gamma times L to the alpha, we're going to achieve our objective of making beta smaller. Beta of 0.6 was too big. Now beta is going to be gamma smaller than what it used to be. So the Romer solution is going to produce a value of beta that's smaller and get us to our goal of getting a 0.6. Another attempt to get us an endogenous growth theory was that of Mankiw. And Mankiw said, instead of changing the technology factor, he's going to keep technology as a function of time, but he's going to add this new factor called human capital. Human capital is shorthand for both education and health of the workforce. And he's just going to throw it onto the equation and say, same old Solow model, but now we're going to add a human capital measure, and we're going to estimate that same Solow model with this third factor, gamma. Some empirical tests done by Mankiw found that alpha would be 0.3, beta was 0.3, and the returns to human capital were 0.3. So now we have a fix, we have a model, a growth theory that actually does what we want. It finds us a set of values that fit the world a lot better than before. We still have some paradoxes. Just as we predicted that there would be convergence, where economic factors would travel to where they were scarce, we have paradoxical observations in the Mankiw model. The Solow model and the Mankiw model predict that labor would travel to areas where labor is scarce. That for sure is true. That's why there's immigration. That's why laborers are moving to where they are needed in the global economy. We commented that capital does try to go to areas that need capital, but is sometimes inhibited by obstacles to its flow. Now, in terms of human capital flows, people with PhDs and lots of health, do they go where there are very few PhDs and not much health? And the answer is no. In the Mankiw model, people with lots of human capital try to go where there's more human capital. So this is new. We don't have a way of moving our human capital to places that need it in the Mankiw model. I want to end by showing one of the best features of these new endogenous growth models. They have this way of solving the old stagnation of the past. With our endogenous growth models, we get this new version of our production function. In the NeoClassical model, we assume that the human capital per worker would always be 1, and we would be stuck right here. What happens in the Mankiw model is this is a graph of GDP per capita and the quality adjusted labor input. And now because the quality adjusted labor input is adjusted by H can grow. Because H can grow, because human capital, our schooling and our health can grow as a function of our GDP per capita, we no longer hit the wall of subsistence like we did before. I'm going to pause a little bit just so you can see it. Quality adjusted labor is this new factor input. It's not labor that makes the output, it's quality adjusted labor, the output here of GDP per capita. So this third phase helps us escape from our stagnation point. And what we can see is instead of having our classical stagnation where we hit the wall and stay in starvation or subsistence forever, or as in Solow, if we come to a place where our capital labor ratio won't grow, in these endogenous growth models, we hit this third phase where the output can grow faster than our labor force, and we can have continued growth of the economy as long as we keep making sure that the human capital can grow to some extent. Obviously, we cannot be infinitely healthy and we cannot be infinitely educated, but for now, we're in a potential phase where our output can grow faster as human capital in the world is growing and education and health continues to grow. So let's go over the main points of today's lecture. All of our models had to wrestle with there being diminishing returns. All of our models had a focused policy implication, and they all had some limits. And a lot of the limits had to do with the way they ignored political, institutional, and social factors. They're caricatured. Remember how Lewis just said that industry can always absorb labor and labor can always migrate, and all of the political forces behind migration were covered over. The Solow model said as a residual term, so much of growth is being driven by something that I don't even know what it is. It's in the residual of the statistical model. And there was limited attention at the beginning of the Solow residual actually being political and institutional. So we're going to fix those limitations in the later part of the course, but growth theory tended to not fix the problems of leaving out politics, institutions, and social factors. Now, there were policy messages for sure. In the classical model of Malthus and Ricardo, the classical policy message was to save. In Coale-Hoover, that model led to the policy prescription of both saving and contracepting to stop the population growth. In the Lewis model, because migration into this industrial sector was the force that was driving growth, the policy message of Lewis was to build the industrial sector. The NeoClassical model said that there should be convergence, that capital needs to go to where it's valuable, just like labor needs to go where it's valuable, and neoclassical economists were trying, and are still trying, to solve the things in the world that stop capital from going where it's needed. You can imagine how a neoclassical economist might have been a very important force in creating the World Bank and the International Monetary Fund, this idea that capital needed to flow. And I think those neoclassical economists today would be very excited to know that foreign direct investment was indeed flowing to solve scarcity in the capital markets. So the final policy message was this endogenous growth policy message, which was to invest in human capital and to make sure that human capital growth keeps up with the growth of both labor and machine capital. So policy messages continue, these normative effects of the work of economists continue, but I think the limitations are looming, and we need to move on in our thinking to a place where we are no longer leaving out our policy messages to focus on institutions and politics. Thank you very much for listening to this lecture.